Welcome to the Elon Musk Signal channel. Recently, Elon Musk once again drew the world's attention to SpaceX with the proclamation that Starship is the most powerful aircraft ever. With 6 Raptor engines on its main body and 33 engines on the Super Heavy booster, SpaceX's ambitions don't stop there. Starship is designed to be a reusable vehicle, paving the way for more cost-effective and sustainable space travel. Musk even revealed plans to upgrade Starship to achieve triple its current thrust, adding more engines to both Starship and Super Heavy. So, what colossal upgrades will SpaceX implement? Is this the final version serving SpaceX's missions to explore the Moon, Mars, and beyond? Let's explore in this video. The developmental history of Starship also illustrates SpaceX's relentless ambition. While researching larger versions of Starship, SpaceX deliberated over various engine configurations for the Super Heavy booster. Choosing the number of engines for Super Heavy wasn't simple. SpaceX engineers factored in the complex design of the Raptor engines and how to arrange them to efficiently allocate thrust for the rocket. After much consideration, SpaceX and Elon Musk settled on the optimal number of 35 Raptor engines, with the potential to expand to a maximum of 33 engines on the final version. With 35 Raptor engines, each producing over 280 tons of thrust, the Super Heavy booster achieves a total thrust of 10,000 tons. This figure surpasses the legendary Saturn V, the rocket that once propelled American astronauts to the Moon, by threefold. Moreover, the Super Heavy booster alone stands at 80.2 meters tall, equivalent to a 30-story building, towering over the Statue of Liberty by 18 meters. Beyond possessing the colossal Super Heavy booster, Starship V3 impresses with its upper stage. True spaceship, pivotal in propelling humans beyond Earth's skies. It's equipped with 9 Raptor engines, along with extended fuel tanks, allowing Starship V3 to carry an additional 300 tons of super-chilled liquid oxygen and methane. This increases the total payload capacity to nearly 1,600 tons, equivalent to a 40-story building, quadrupling previous test models. After separating from the Super Heavy booster, Starship will reach a height of approximately 70 meters. The power of Starship V3 doesn't stop there. This upper stage will utilize 3 Raptor engines optimized for vacuum conditions and 6 Raptor engines optimized for sea-level conditions. This combination is expected to generate a minimum thrust of 2,700 tons, potentially even higher depending on engine performance. To illustrate, this thrust is equivalent to the power of 18 Boeing 747 aircraft engines, the queens of the skies in the era of commercial aviation. Compared to the standard version with 6 engines on the upper stage and 33 engines on the booster, the new masterpiece Starship can significantly enhance payload capacity, from 150 tons to over 200 tons when launching into Earth orbit. This represents an improvement of nearly 50%, a substantial leap forward. Regardless of thrust, size, or weight, Starship V3 is truly a behemoth, poised to break all limits to conquer ambitious space journeys. With its capability to transport large payloads and carry humans to the Moon, Mars, or even beyond, Starship V3 promises to usher in a new era of space exploration. Unlike traditional aerospace giants, SpaceX is renowned for its motto, "Failure is a lesson," turning test mishaps into breakthrough victory. They don't follow the trend of colossal rocket engines, but instead opt for smaller, more flexible engines. This choice is persuasively linked to the rocket's reusability, a core factor in reducing costs for space missions. Reducing the thrust of traditional rocket engines is extremely challenging. Similar to suddenly reducing throttle in a car, rocket engines can shut down completely if thrust drops below a minimum level. This poses a challenge during the phase when the rocket needs to accelerate massive payloads to extremely high speeds. Take Starship, for example, with a mass of 100 tons, but requiring 1,200 tons of liquid methane and oxygen fuel for launch. During liftoff, rocket needs to accelerate the massive 1,300-ton payload to extreme velocities. The smaller engines from SpaceX effectively address this issue. They can adjust thrust flexibly, aiding the rocket in controlling the acceleration process better, especially in the initial stages when fuel mass is significant. Additionally, the design of multiple smaller engines provides advantages in flexibility. In the event of an engine malfunction, SpaceX engineers can easily replace individual engines, saving time and cost for maintenance and repairs, thus ensuring the timeliness of critical space missions. Furthermore, employing numerous smaller engines allows SpaceX to distribute thrust, reducing the load on the rocket's structure. This enables the construction of rockets with lighter materials, further saving weight and enhancing overall efficiency. Imagine a giant engine that can operate between 20 to 100% of its power. However, if it drops below 20%, it will shut down completely. For a massive rocket like Starship, this would be catastrophic during the landing process. At that point, the rocket needs to significantly reduce thrust, from the power needed to propel 1,300 tons into space, to just enough to safely land on the ground. If there were only one giant engine, reducing thrust to 20%, approximately 260 tons, would still be too much, causing the rocket to ascend instead of landing gently. Moreover, continuously forcing the engine to operate at low levels can cause damage and reduce lifespan. In contrast, with the strategy of multiple smaller engines, SpaceX can be much more flexible. 4 Raptor engines, each capable of providing 1/4 of the required thrust for launch, about 425 tons, offer the ability to adjust thrust more precisely. Instead of reducing the power of all engines to 10%, SpaceX can shut down 3 engines and maintain only 1 engine operating at 40% power. This ensures sufficient thrust to control the landing process safely, even with rockets like the Falcon 9, which uses 9 Merlin engine. Using multiple smaller engines allows SpaceX to flexibly adjust thrust, optimizing both the launch and landing processes of the rocket. During the initial launch phase, all engines operate simultaneously, generating enough thrust to propel massive rockets like Starship beyond Earth's gravitational pull. As the desired altitude approaches, engineers can adjust, shutting down some engines to conserve fuel for the long journey. Conversely, the landing phase requires less thrust to gently touch down on the ground. At this point, shutting down some engines and maintaining one or a few engines operating at appropriate power levels is the optimal solution. This strategy not only helps SpaceX land rockets safely, but also significantly saves fuel. Furthermore, using multiple smaller engines provides advantages in mass production. SpaceX aims to produce thousands of Starships and hundreds of Super Heavy boosters, requiring tens of thousands of Raptor engines, a massive number in the history of rocket engine production. Advanced 3D printing technology helps SpaceX manufacture Raptor engines at a reasonable cost. Additionally, the design of multiple smaller engines simplifies the production process compared to manufacturing giant engines, meeting SpaceX's mass production requirement. Although the launch schedule may sometimes be delayed, Elon Musk is still fulfilling promises regarding Starship. Both SpaceX and NASA are betting on the future of this giant rocket, hoping it will fly safely and take humans back to the moon. And that concludes today's video. Stay tuned for more exciting events from SpaceX in the journey to conquer space. Thank you for watching. Don't forget to leave a comment and hit the like button if you found the content helpful. Remember to subscribe to the channel and turn on notifications to await more interesting videos on the Elon Musk Signal channel. Goodbye, and see you again.